Warm good evening to everyone. So, welcome you all for the fifth day AICT ATAL sponsored FTP on foundations and application in quantum computing from qubits to quantum entanglement. So, we'll start with today's introduction with a resource person, Dr. P. Satyaprakash. So, he's a distinguished guest today. He's a chief operating officer of Anutantra Private Limited, also an eminent academician and a researcher with a profound expertise in quantum computing, artificial intelligence, and wireless sensor networks. So, Dr. Satyaprakash has over a decade of teaching and research experience across reputed institutions, including the School of Computation at Shastra, deemed university, then Calcutta University, and Mahabharati Engineering College. He holds an PhD in Information and Communication Engineering from Anna University, Chennai, and is currently pursuing a joint certification program in AI and quantum computing from QPI and IISc Bangalore. So his research interests span across the quantum machine learning, optimizing algorithm, and the quality of service enhancement with wireless networks, with a numerous publication in reputed journals and conference such as IEEE, IET, and ACM. So alongside, his scholar contributes also holds multiple patent in autonomous and wireless sensor networks. So a passion educator and mentor, Dr. Satyaprakash has guided several students, many of them whom are now placed in the leading companies like ATAL. He also been and actively involved in international conference workshops, not only as a participant but also an speakers and associate editors. Dr. Satyaprakash has played a private role as a resource person in AICT sponsored ATAL FDPs, as well as workshop and conference on quantum computing, neuromorphic computing, and AI at esteemed institutions. So his international contribution are equally worth with a section delivered on quantum machine learnings and quantum mechanisms under the platforms like National Quantum Missions, IBM Educations, and TQCBT, including their special program in Ghana. So we'll invite our resource person, Dr. Satyaprakash, and heartfelt welcome to this section. And thank you very much, sir. Sir, welcome, sir. Satyaprakash, sir.
Satyaprakash sir? Sir, are you on the line? Sir, please unmute yourself, sir. He is on the live. The mic is muted, sir. அவரோட வாய்ஸ் கேட்கலையே. Satyaprakash sir, are you on the line? Audible இல்லையாமா? கால் பண்ணுங்க. Sir, Satyaprakash sir, am I audible, sir?
Meeting is being Yeah, now am I audible?
Yes, sir. Yes, sir. You're audible,
Yeah,
sir.
actually, I was using my mobile's internet. There is some problem with the broadband, it seems.
Yes. No problem, sir. Please
Yeah,
continue, sir.
yes, it's a pleasure to be here. So, I think you people are hope enjoying the quantum workshop series. So, how was yesterday's session with biscuit demonstration from Dr. VJ?
It was a clear definitions explanation given in that open source tool, sir. Really good, sir.
Okay. Yeah. I heard the same feedback from Dr. VJ. Okay. Yeah. Now let us see some quantum applications and again some little more in depth. Okay. Now let me share my screen. Right. Now it is. Now my screen is live there.
Yeah, yes, sir, yes, sir.
Yeah. So we will dive into quantum computing and quantum computing applications. Right. So in last couple of days you might have heard about quantum computer, right? So quantum computer is a QPU and a combination of classical computing interface. Quantum computer is not a standalone computer. It is a combination of QPU as well as classical computing interface. Right. Then how we are representing the quantum bits. In short, it is called as qubits. See, later I will show the representation of qubits in the OneNote, the mathematical expressions. I think most of you people aware already. Still, I will show you. Then the important aspect in any quantum computer is controllable unitary evaluation. Why? Because the random variables of the quantum computer is going to be the type DRV. So DRV stands for discrete random variable. So you know about the discrete type. So either Bernoulli or binomial. It takes two outcome, 1 or 0, yes or no.
Sir, excuse
So
me, sir.
if you cumulate, yeah,
Sir, your slide is not changing, sir. It is still remaining in the
slide is
first
not
slide.
changing.
Yes, sir. Please move on to the full screen show, sir.
Full screen. Okay, okay, okay. Let me see. Share your screen sharing. Now, now it is visible.
No, sir, it is only on the first slide, sir.
First slide. Now also.
Yes, sir. Again, it is on the first slide.
Okay. Let me do one thing. I will not go for now.
Yes, sir. Sir, now it is changing,
Slides
sir.
are changed. Yeah. So kindly bear with me. I am not able to fix in quick. Yeah. This is the slide which we are discussing. See, quantum computer is not standalone. It is hybrid. I mean, it contains QPU as well as classical compute interface. Then, how quantum bits are represented? So, based on that only, the size or the type only decides how we are going to utilize in normal room or specific climate control. It is based on that only. The qubits are generated and the thing. Then controllable unitary evaluation means most of the quantum computing variables are not most, the random variables are going to be discrete random variable. So because it is going to be discrete random variable, we insist unitary evaluation. The total probability of the system will be always 1. Then the first step, how all the qubits are initialized, the preparation of initial qubit states. So typically it is called ket representation. There are two. The one is called ket, the another, the conjugate is going to be bra notation. Ket as well as bra notation. Then the final output is going to be, so in classical we are running. So in quantum computer, no such terminology. In quantum computer, no such terminology. It is called measurement. It is called the measurement. So it means what is the information found or what possessed inside a qubit. Typically it is the state. So measurement of final qubit state. So collapsed to either state 0 or 1. So this R is English or, not logical or. Either state or 1, yeah, we can say logical or. Definition wise 0 and 1. Definition wise 0 and 1. Once it is collapsed, 0 or 1. So it will be classical. So that is the reason. If you look at the any visual representation of quantum computer, you can see waves in the first compartment, second and third. Only in the last compartment you can see arrow mark. Wherever you see arrow mark in the quantum computer schematic representation, it is digital. It is going to be digital. So so there is a power cut here. Let me disable my video. Right, so this is a typical image of any quantum computer. So this is of type superconducting qubits. This image is from superconducting type qubits. So typical image of any superconducting type quantum computer. Right. Now let us see the first component is QPU. The first part of the quantum computer is going to be the quantum processing unit. So quantum processing unit, that is a vital component where all the computation takes place. Quantum computation takes place. So how it looks like? It looks like a chip, shiny metallic surface. QPU is always going to be a in superconducting quantum computer. The chips looks shiny metallic surface. So there all the concept of qubits which process, and there it holds the information. All the quantum computation takes place inside the quantum processor. Then if you look further, there you can see tiny lines, and loops are drawn. I mean, it's not drawn, it is arranged in the surface. So those are microwave resonators. Those are going to be microwave resonators. Generally, you people hear quantum computer, generally it will be of type superconducting qubits. In later parts, I will show you which is superconducting, trapped, and etc. So this is typical part quantum compute, quantum processing unit. The next, the component which you see in any, there will be a cylinder like structure. There will be a cylinder like structure that will be called as dilution refrigerator. Suppose we are using superconducting type, it requires special environment. So that is the reason we are not able to see any computers in rooms, in room. Why? Because for that we need cryogenic setup. That cylinder is technically called dilution refrigerator. Typically we can say it is cryogenic setup. So the dilution refrigerator's job is to cool the quantum processor. The ultimate job of any dilution refrigerator is going to be cooling the quantum processor. So that's why people used to say the coldest places in the universe is not any physical place which is available in Russia, Antarctic, Arctic regions. It is going to be the quantum computer which is available in US, IBM lab, Boomerang Nebula. That is what they say, that place called Boomerang Nebula. That is the quantum chip inside the dilution fridge. That is the quantum chip in the dilution fridge. So it looks like the cylindrical device. So it height ranges from 4 feet to 5 feet. Ranges from the height of the dilution refrigerator ranges from 4 feet to 5. So there are refers height of a human. So inside there are multiple layers of shields. These get progressively colder from bottom to top. If you go upper, what happens? Progressively colder. It isolates the processor from heat and electromagnetic noise. So this is the dilution refrigerator. So how it works? Progressively it gets colder. Progressively it gets colder. Next, the next one component which is present in that is control electronics. We have seen QPU, then the surrounding environment. The next one is control electronics. So the control electronics, the base is going to be microwave electronics. Microwave electronics that is used to control the quantum information bit. They send microwave pulses to the quantum processor to perform calculations. Here only calculations were carried out with the help of control electronics only. The calculations were carried out. Then it converts quantum algorithm into instructions. So we computer science people know, right? Instructions are what? Line by line execution of the program codes are going to be our instructions. So these control electronics, they are connected to the dilution refrigerator through thick cables. So like, right, so these are all thick cables. They are connected to dilution refrigerator through thick cables. Next, as I told earlier, quantum computer is not a standalone computer. It is always going to be hybrid computer. So that is what the last part of the, in the schematic representation, if you see, there is a arrow mark or a circle like thing, you can see that is the portion of classical computing interface. So there we do measurement process. There we do measurement process, converting any quantum state into classical state, or we can say directly classical data. So then control, so generating signals, so microwave pulse to manipulate qubits, then signal conditioning, processing and amplifying signals for accurate measurement. Accurate measurement, this terminology is important, measurement. So there is a beauty in quantum computer. It is possible to bring different outputs from time to time. That is possible in quantum computer. So that is what they mean here. Amplifying signals for accurate measurement. Data processing, so performing calculations on the classical data to guide quantum computation. So this is the job of any classical computing interface. Right here, let me stress mathematics of quantum computing. Right, whenever you people, if you go through any literature, any books, any articles, right, there you see mostly what, some notations, right? Say yes or no, participants. You see several notations, that is get notations. So with get notations, what we represent, any guess, participants? I will show you now. Let me share. Is it visible? Yeah, I'm asking about this one. So what is this? That is, whichever this symbol is called get, this is the quantum state. So whenever we do any operations, it takes place between quantum states. Takes place between quantum states, right? So that is the reason it evolves. Sorry, it is surrounded by linear algebra, trigonometry. I think yesterday you must have seen block sphere. Block sphere is used to visualize the quantum information inside. Probability and measurement, quantum entanglement. No, there are many, but among multiple parameters or mathematics component, these are all highlighted: linear algebra, trigonometry, probability, quantum entanglement, Fourier transform, and complexity. Next, right. So, if you ask me the definition of quantum computer, I I may say it is tensor calculator. What is it? Quantum computer is going to be a tensor calculator. Any guess, participants? Put it in chat box. Literally, we can say quantum computer is a tensor calculator. Tensor calculator. CULATO. Any guess why the quantum computer is otherwise termed as tensor calculator? Is it visible? Look at here. This symbol is called as tensor operator. This symbol is called a tensor operator. If you take tensor between two, tensor product is going to be a vector. Otherwise, Kronecker product. Look at here. Why tensor operator is important? Because quantum states are represented by using tensor operator only. Here we are taking tensor between state 0 and state 0. Product will be 0 0. In order to represent, this is the representation of state 0. This is the state representation of 0. Tensor of 0 0 will be 1 triple 0. So this is the 2 qubit representation. 2 qubit representation. Next, if you take tensor between state 0 with state 1, typically it ends in 0 1. Representation of 0 and 0 1. Obviously, the output is going to be 0 1 0 0. 2 qubit representation. First qubit and second qubit. In total, this is the way, like, right. You can try tensor between state 1 and state 1. What it would be? Next, tensor between state 1 and state 0. I think this is going to be, any guess? Tensor of, with respect to 0 0, it is 1 triple 0. 0 1 0 1 double 0. What about 1 0? 0 0 1 0 is going to be 1 0. What about 1 1? Right. So work it out. This is why quantum computer is going to be a tensor calculator. Tensor, yeah. Let me stop here. Look at here. What is this? This is a single qubit gate called Pauli gate. Pauli X applied to state 0. Then what happens? Then what happens? Input flipped to 1. This is Pauli matrix. This is Pauli matrix 0 1 1 0 with state 0. The resultant is going to be state 1. Right. Likewise, what we are doing with the help of Pauli X gate, applied it to state 1. Then what will happen? Obviously, it flips to 0. Pauli matrix, then state 1 result in state 0. So this is a sample single qubit operation. This is the definition of quantum computer mathematically. So this is the reason operation reversible. Quantum computing operations are reversible. Indefinite state, exponent in size of input. Look at here, why 2 to the power n? The state space of any quantum computer is going 2 to the power n. Why? Why? Why 2 to the power n? 2 power n. Why state space of any quantum computer is going to be 2 to the power n? Friends, yeah, put it in chat box. Why 2 to the power n? So here 2 is the definition of quantum computer, 0 and 1. There will be two states and n will be number of qubits. So 2 to the power n means single qubit and there will be two states. Suppose two qubits will be there, then how many state space will be there? 2 to the power 2 is how much? 2 to the power 3. Super. Suppose there are 3 qubits, then how many states will be there? 8 states will be there. 0 0 0 0 0 1 2 triple 1. Super, super. There is somebody, he got the flavor of quantum computing, right? Look at here. If somebody wants to note it down, right, this is 3 qubit representation. Qubit, 3 qubit. 0 if it is decimal, 0 1 2 3 so on. 0 0 quantum state, 0 0 1 0 1 0 0 1 1 so on, right? Let us go back, right? So this is what written here. State of qubit completely described by unit vector in Hilbert space. The problem comes when if there is one more than one qubit, right? If there always what? 2 to the power n, always minimum will be single qubit. Single qubit is for namesake, theoretical. So there will be always what? We should put qubits into entanglement. We should put what? When we can able to see the beauty of quantum computer, if we project the qubits into entanglement, then we will enjoy the extra computation. Comes only when during entanglement. In entanglement always there will be two qubits, right? This is what I have shown earlier. Single qubit gates. See, quantum computer is all about what? Gates and gate operation. So quantum computer, earlier I told the definition, then parts of a quantum computer. Now what? How quantum computer operates? So single qubit gates and multiple qubit gates. So single qubit gates as well as multi qubit gates, right? Is it fine? So what? Single qubit gates as well as multi qubit gates. So what are all these gates? Anybody knows from the participant side? Say, put it in chat. Few gates, few quantum computing gates. Yeah, super, super. Hadamard, very good. Hadamard, super. C not, yeah, super, super. Right, right, right. So few are single qubit gates. C not, among this, C not is going to be multi qubit gate, right? So later I will show you how C not works and Hadamard works. Yeah. See, this is single qubit, right? So now tell me, what is this? Hadamard gate is represented by Hadamard matrix. This is Hadamard matrix. Then what is this? I differentiated with double color. This the black one is going to be the matrix. The blue one is going to be the, what is this? The blue. Anybody from the participant? What is it? Blue. Super, super. The blue is going to be the state. So the gate along with the state produce what? Produces quantum computation. Produces the quantum. So always h of state 0 is what? H of state 0 is going to be state plus output of Hadamard operation. Hadamard 0 is what? The output of Hadamard 0 is going to be plus. Right. Now I will give it to your choice. Output of Hadamard 1. What is the output? Quantum output of Hadamard operation state 1. Said we ket minus. Super, super, super. It is ket minus. Right. Definitely you people will rock in quantum computing, right? So this is the working of Hadamard gate. Right. Next, the important qubits are going to be, right. So the important phenomenon is what? Entanglement. As I told earlier, entanglement. So how to achieve entanglement in quantum computer? So in order to achieve entanglement in quantum computer, we need two qubits. We need what? Two qubits, namely control qubit as well as target qubit. Control as well as target. So what is this? So C naught is the equivalent of XOR gate. C naught is what? C naught is an equivalent of XOR gate. So Q1 and Q2. This is a typical structure of C naught. In the next slide, I will show how quantum operation using C naught will happen. Right. So what is the theory? If the control qubit is state 1, then what is it? If the control qubit is going to be 1, the second target qubit is flipped, or else it is remains unchanged. Yeah. Look at here. I think you people able to see, right? So this is Q1 and Q2. So what is a theory which is unchanged? If the target is going to be 0, then what is happening? There is no change in the target, right? Look at here. When control is going to be 1, then what will happen? The target will be flipped.
And expensive. And why does it take so long? It really shouldn't be that. Get started in SOA, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. Fit SOA's your needs. It's simple, quick, and free. It's security done with SOA.
So what is that? There is some external noise.
ಹರಪ್ಪ ನಾಗರಿಕತೆಗೆ
please
ಸ್ವಾಗತ.
mute yourself, madam.
ಇದು 5,000 ವರ್ಷಗಳ ಹಿಂದಿನ ನಾಗರಿಕತೆ.
Sir, mute kodunga. Sir, please proceed, sir. Sir, Satya Prakash, sir, please proceed, sir.
Yeah.
Yes, sir. Thank you.
No, yeah. So yeah, it's okay. Sometimes it used to happen. It used to happen for quantum computer also. Right. Now the slide is visible. Now my slide is visible. No. Slide is visible.
No, sir.
Slide is visible or not?
No, ma'am. No, ma'am. Not at all.
No,
sir.
Now.
No, sir. No, sir.
No,
We
ma'am.
are unable to see the screen, sir.
Yeah.
Yes, sir. Now it is opening, I think. Your name is visible. Yes, sir. We can able to see your slide, sir.
Now it's visible.
Please proceed, sir.
Voice not audible, sir.
Sir, no audio, sir. Sati Prakash, sir.
Yeah, no, yeah. By mistakenly I unmuted. Yeah, now. So this is the operation of CNOT. Is it fine? This is the operation which generates entanglement in any quantum computer. CNOT combination of Hadamard plus CNOT leads to entanglement. Right. Look at here. This is the operation. CNOT can be represented by the matrix and the state 0, 0. CNOT, one sample operation of CNOT, the matrix and its state. Right. Look at here. So this earlier I told, and you might have doubt with the single qubit. You have any idea how much information we can hold? 512 bits. With the help of single qubit, we are able to handle 512 bits. And in a qubit, we have two basis states. One is state 0 and one is state 1. Next, suppose we are having 2 qubits, we can able to hold 1024 bits and basis states 4 and representation is state 0, 0, state 0, 1 and so on. So like 3 qubits, 16 kilobytes and its representation state 0, 0, 0, state 0, 0, 1. So any guess how many qubits we can have n? But as of now, with the help of more than 150 qubits, we can hold the information of our entire galaxy. Sorry, 128, we can hold information of planet Earth. With the help of 256 qubit, we can hold the entire information of our galaxy. That is the capacity. Tensor. So keep on what access 2 to the power n. This is the beauty of 2 to the power n. Right. Then you might have a question. So how? So like classical in quantum also we are having quantum register. So multiple qubits forms a quantum register. The number of computational state doubles with new qubit. This is the beauty. The number of computational state doubles with new qubit. State with multiple qubit involved is often denoted by tensor product. So this is the reason if we wanted to work with quantum, we should know tensor or Kronecker product. We should know tensor or Kronecker product. So it comes into picture when we need to perform quantum registration process. Registers, right? So we have seen the basis states. So likewise, this is a combination, right? Now this is the type of quantum. So you have any guess how many types of quantum computer available? Any guess how many types? So we have 5 to 6 types of quantum computing are there. 5 to 6. The the most familiar one, not famous. The familiar one is superconducting type. The quantum bit, the principles of quantum mechanics achieved by superconducting process. The next one, cavity, we can say quantum emitting diode, or else we can say QLED, photonics quantum computer. This one is photonics quantum computer. Next, trapped ions is another type of quantum computer used to generate quantum mechanics. Then qubits will be constructed. Charged atoms. Charged atoms are responsible for trapped ions type of quantum qubit. The next one is neutral atom. Several components are called as neutral, so they will not have any charges. That also, that quantum mechanics principle leads to generate quantum information bit. That is one type. The last one is nuclear spins. We can say it is NMR, nuclear magnetic resonance type. So we can generate strong magnetic field with the help of NMR. Then with the help of those hydrogen numbers, those will be directly proportional to quantum bits. So these are all various type of quantum bits: superconducting, cavity, trapped ion, neutral, and the nuclear spin. Definitely you might be interested. In the next slide, I will show you who are all the players. Yeah, these are all the qubit ecosystem and their players, right? Like we have discussed earlier, superconducting used by IBM, Google, Rigetti. Materials are quantum materials are going to be aluminum, niobium. This is the reason these computers cannot be seen in normal rooms. So we need special setup called cryogenic setup is required for maintaining this temperature -273 1 degree Kelvin. This is 1 degree Kelvin. Next, trapped, manipulated with laser. So who is the selected player? Honeywell, Ion. These are all the players. They are having quantum computer of type photonics. They use light, not photonic, trapped ions. Photonics are particles of light used by Xanadu and Psi quantum. Neutral atoms. I told right earlier slide. I told the neutral atoms are helium and nitrogen used in these kind of qubits. Quantium and Dirac. These are all the companies which is using these type of quantum computer. So I think we know these two only, IBM and Google. So there are many: Rigetti, Honeywell, Ionic, Xanadu, Psi quantum, Quantium, and Dirac. So various types of quantum computing. Various type of quantum computing. Yeah. Now this is the slide. We will see why the computation edge is popular because of these phenomenons: interference and entanglement. These two principles are the main achievement from a quantum computer. The principles of interference allows a quantum computer to cancel unwanted solution. This is the reason if we repeat the number of experiments, what happens? It enhances the correct solution. Please make a note. This interference only what does? This interference only allows computation to generate correct solutions. This is the highlighted thing of any quantum computer. So entanglement, as I told earlier, combined state of qubits contains more information than the qubits do independently. And one more thing, you people heard about quantum. So when we can say any quantum application is going to be quantum, it will be 100 qubit. If a quantum computation use or utilizes 100 qubit, that will be purely quantum. There only we can see the advantage of quantum computation. Less than 100 also, but where we can see, when we can see means if we use more than 100 qubits, then only we can see the real potential of any quantum computer. Real potential of any quantum computer, right? Then as we seen earlier, there are multiple players are there in quantum field. IBM, Xanadu, Google, and Microsoft, they have their own tool. IBM is having quantum information science toolkit. Xanadu is having Pennylen. Google is having Circ. Microsoft is having QSharp, and so on. So there are few others also. In order to limit and a compact slide, I have used only these four: Biscuit, Pennylen, Circ, and QSharp. Still, we have Strange and etc. Strange, and in Indian in CDAC we have a quantum simulator, and I think it is Q control. I think it is Q control. So, so various software used for quantum computing: Biscuit, Pennylen, Circ, and QSharp. So among this, Qiskit is having variety of application. It covers wide range comparing. If you ask me machine learning, you can use Pennylen. I didn't mean Qiskit will not solve. Pennylen is simple. If you want to execute quantum machine learning applications or problems, better you prefer Pennylen. Better use Pennylen. For Qbal, both Circ and Pennylen. Right. Now we enter into the what hard topic of this today's lecture. Right. Look at this slide. Take 2 minutes. Look at this slide. In chat box, give me your comment. What do you think about the quantum application? Yeah. Look at this and give me your comment. So what is here? You can able to see what in this slide. It it covers all, right? It is purely interdisciplinary. We can apply quantum computing to all the, like sister airlines, banking, and financial, chemical, electronics, government sector, healthcare, insurance, life science, logistics. See, government, here I need to highlight one thing. See, nowadays the developed nations are planning to keep their standard to post quantum cryptography. What they are planning? Post quantum cryptography. So what it means? What? Suppose our data is our information is compromised, it should not be decoded. It should not be decoded. So what China is now doing is they are stealing information from most of the countries. From US they have started what? You know about the Huawei problem. Most of the US government hardwares are going to be from Huawei. From India also they are what? They are stealing our information. So their plan is to record now, decrypt later. Note a point. What is quantum cryptography is inserted? They are stealing our data now. When their quantum computer is going to be very strong, that time they will decrypt all our data. They are stealing the data right now. Okay, when their quantum algorithm and things are going to be heavy and exceptional, that time they will decode all our, so like India, France, US, they have Chinese people are having all our data. So that is what all the governments are what planning to be post quantum cryptography. So this is one highlight I wanted to specify here. Healthcare, insurance, life science, and logistics. Right. Then and one more. If you ask the revenue, the major revenue is from, suppose if it is 100 rupee, 60 rupees is coming from chemic quantum chemistry only. Suppose income is, statistics is analyzed, statistical income of quantum is calculated, majority of the income comes from quantum chemicals only, quantum chemical industry, not from computing. It is from, like, pharmaceutical industries are generating more revenue through quantum computers. Sorry, quantum computers generating huge revenue from pharmaceutical companies. Right. Now we will see the interesting applications. Right. Most of the computer science people are very much interested to know, right? Quantum machine learning, right? Yeah. And this is the beauty. IBM and HSBC Bank Corporation developed a hybrid model. IBM and HSBC developed a quantum hybrid model for effective risk classification, fraud detection, consumer behavior modeling. So that is one aspect of QML. It improves predictive model fusion. So what it did, it better predicted financial data sets using IBM quantum system. So they used HSBC's data set. Then what they have done, created a hybrid method combining several quantum kernels into one. They predicted better. It predicted better. One famous quantum computing application. Right? Note it down. QMKL, combination of multiple quantum kernel. So who and who? IBM and HSBC. Next, the next interesting application is going to be Ionic with Hyundai. Ionic with Hyundai. So this is a huge improvement in self-driving cars. This is a huge improvement in self-driving cars. So what Hyundai did, with the help of Ionic, they did image classification, the 3D object detection. So look at the image. Their their autonomous cars effectively classified and detected using quantum machine learning. So the process is, they encoded the images into quantum states. They encoded the images into quantum states. And how many data they have used? They have used 43 types of road signs. I think in road we have seen the signboards, right? So if the self-driving cars is able to recognize 43 types of road signs. So it is a huge breakthrough in autonomous vehicles. So one famous application of quantum computing from Ion and Hyundai. Right. Next, another one. So it is with D-Wave is one famous quantum computing, and it is the software which is used in port management. D-Wave and 7tex. So what they have did in US, Los Angeles is having a huge port. There they have handling huge cargoes in that port. So there they have used cranes to fit trucks. Then what it happens? There is a problem with the labor. Finding the what cranes to fit trucks is the huge problem of 7tex. So for that, D-Wave provided a quantum annealing method to solve the challenging labor issue. So what they have done, the D-Wave provided quantum annealing to effective handling the scheduling of cranes to truck. Means what? They effectively find at the cranes to fill the truck. So 7tex created hyper optimized nodal efficiency engine. This is the name of that particular one. Hyper optimized nodal efficiency engine. So what is the objective? The objective is to simulate the Fire 300. This is the software which is used in 7tex. This is the software which is used in 7tex. Right. So what it does? It handled, look at the number. This is what? 1 million cargo scenario. So Fire 3 is what? Is not able to manage 1 million. So with the help of that horn, they managed 1 million cargo handling scenario. So horn supplied at Fire 300 produced amazing results. So means what? If it is amazing means what? Cranes operated with efficiency, one of the most notable development. Results in improved efficiency of the terminal. So where it is beyond logistics, this is used in airline scheduling, urban traffic optimization, and it is also used in network design, especially in telecom industry. Quantum computer is what widely used apart from logistics, airline scheduling, urban traffic optimization, network design in telecoms. So another notable quantum computing application. Right. The next one. The next one is what? Again, IBM quantum computing and Moderna. I think you people know about this Moderna pharmaceutical company. The researchers used IBM Eagle and Heron quantum processors to solve mRNA structure. This is one famous application to predict sequence predict sequence. So if you predict sequence, what will happen? We can generate what? vaccine. What it will do? With the help of that, we can generate vaccines. So they employed the quantum eigensolver algorithm, VQE, variational quantum eigensolver algorithm, which is generally designed for optimization problem. Like we can use route optimization, logic optimization side, so we can handle various optimizations. This algorithm helped in which field? Used in pharmaceutical field. Variational quantum eigensolver algorithm to handle optimization problem. So in this they focused on mRNA sequence up to 60 nucleotides. These are all pharmaceutical terminology, but how many number of qubits? For this they have used range of 10 to 80 qubits. So look at here, still it is below 100 qubit. It is not a challenging one for quantum computer. So more than 100 is only going to be what? Pure quantum challenge. When we are going to see the beauty of quantum, suppose we use more than 100 qubits. In this also they have used up to 80 qubits in number. 80 qubits in number. So IBM and Moderna. So what they have done? mRNA sequence. They find effective manage vaccine. Next electronics. Right. I think this is another area where there is a huge income is also generated using quantum computer. Right. Currently, light emitters having internal efficiency 25 percentage means what? So there is only very less. Still, we are struggling to manage the remaining 75% in efficiency. So IBM, Japanese rubber chemical company, JSR is one famous rubber chemical company, along with one more, Mitsubishi, IBM, JSR and Mitsubishi team together to model OLED. This is not QLED. This is the higher most technology available in TV industry nowadays. The starting price of this TV is going to be almost 2 lakhs, I think. I'm not sure, but it is more than 1.5 lakhs, I know. This is the latest TV technology available. So this is developed with the help of quantum computer. IBM, JSR and Mitsubishi team together to model 100% internal efficiency. Earlier, with normal material, they have only 25% efficiency. But what is possible? 100% efficiency is possible. So, what is the statistics says? An OLED display made from these emitters could have power efficiency 1%. 1% increase in OLED display market worth 320 billion per year. So, how much they are generating revenue? These companies market is increased to 1%. It is almost equivalent to 320 billion per year. This is the beauty of quantum electronics application. This is the beauty of quantum electronics application. Right. The interesting part is almost we have arrived. Right. While we are discussing this, I have saying some cost analysis. The 60% comes from this quantum chemistry only. The 60% comes from this quantum chemistry only, right? So there is a famous problem statement: nitrogen fixation. Science people eager to convert nitrogen to ammonia. So what these people are trying? Available problem statement is to convert nitrogen to ammonia. Suppose if it is going to be very effective, then what is possible? Having cost effective fertilizer is possible. Nitrogen fixation, what is required? a better catalyst to convert nitrogen to ammonia. So then it will be a cost effective fertilizer. It will be a cost effective fertilizer. Then next, room temperature superconductor. The next one is room temperature superconductor. I think in today's lecture also you heard about this one, right? Superconductor, right? Where we have seen this conductor. Any guest participants? Superconductor. So it is a famous type of quantum computing qubit. Superconducting qubits. Superconducting qubits, right? So people are interested to find a material that superconducts at room temperature. We have seen it happens in 273 degrees Celsius. Means what? 1 degree Kelvin. It is 1 degree Kelvin, right? That is another problem statement is what? Room temperature semiconductor. If we are able to achieve, we have transmission without loss. If there is such material, so what is achieved? Transmission without losses. Yeah. Yes. Yeah. Yeah. So there is somebody have turned on their mic. Please, could you please? Yeah.
Dr. Mary, please mute yourself.
You just, with your permission, let me have some water. Yeah. Let us proceed. Yeah. We are about to finish. I think there is one more. That's it. Yeah. Let us proceed as it is. Yeah. So with the help of superconductor, room temperature superconductor, so we can see transmission without loss. The next one is the ultimate carbon sequestration. So means we are having enough carbon dioxide, carbon in our atmosphere in the form of CO2. So what they are insisting, suppose if we are able to observe carbon from there, then what will happen? We will control the global warming. It will reduce the amount of carbon dioxide. An effective catalyst for carbon sequestration. Carbon sequestration. Right. So these are all three famous applications. So what it will contribute? It will contribute to global warming. So nitrogen fixation, room temperature superconductor, catalyst for carbon sequestration. So this is a, see, I am not from a quantum chemistry field, but so these are all very familiar in quantum chemistry. That's why they prefer quantum computer. That's why they prefer quantum computer. And all this information which I will deliver to you, so I used to refer from certain online materials and things, but it's all from authenticated places. The one is quantum machine learning unlocked by Xavier Mansilla. Another few important highlights are from programming the quantum computers by Eric or Johnson. Next. So these applications is very tough to explore. So all these are available from Quantum Decade IBM 4th edition. So these informations are available with IBM Quantum Educator, IBM Advocates, Biscuit Advocate, like we used to have. So from there, I collected all those applications and a few other reference. So these are the reference for today's lecture content. See, I don't want to elaborate this delivery end to end. See, I wanted to keep minimalistic, so I cut shorted few. So let us stop here. And my team members, Dr. V. Jaykumar, our Chief Executive Officer, and Dr. Aswath Babu, our CTO, Jinesh, and so and so. And that's it from my side. Happy quantum computing to all the participants and the organizers. Right. So let me stop here and let me take few question and answers if I am able to convey. I didn't mean that I will answer all your questions. If it is within my limit, let me let me tell you. Yeah, put it in your chat box. Let me clarify. Yeah. You have etc. Okay, it says it will be better in quantum computer or quantum mathematics, quantum machine learning. I think people are very curious about QML. So go for classification. Go for classification, not for prediction. In QML, prefer classification using quantum kernels. Using quantum kernels. Sorry. I think so. Let us stop here. Brief about quantum communication. For application point of view, is that data is in the form of qubits? No. So that is the thing. Yeah, I want to clarify. So we are living in the era of classical data, quantum hardware. We need to convert the classical data into quantum states, right? As of now, we do not have quantum data. So we are having classical data and we are having quantum hardware CQ. So we need to convert classical information into quantum states, gentlemen. Quantum communication, see, I'm not right person for quantum communication. Mm, so quantum communication means in quantum communication, so what do you like to know? I think my knowledge of quantum communication is there is a famous professor in Raman Institute called Urbasi Sinha. They work in quantum communication. They do some government unclassified work. They work with warships. They use quantum communication. all I that know. This is the information I know. Quantum materials. See, even I am not so. Graphene is the quantum material which is used in the most of the superconducting material. Graphene, graphene, and there are few new quantum materials. Yeah. So if you wanted to know good about quantum materials, follow professors who works in materials in IASC Bangalore. IISc Bangalore people. They are from where to start my research. I am computer. I have done PhD in image processing. How to relate image processing and quantum? Yeah, you can go for. I as I told you, do image classification. Do image classification. Don't go for prediction. Go for classification. Then evidently, I have seen there is 1/10 betterment is there in quantum training. So means how can we do that? You mean QML? Do PCA. So it is not possible to do because we have very less qubits. So do PCA, then apply, then work it out. Exactly, apply the entire data set and working out will be very complex. Do PCA with the help of PCA, classical PCA, not QPCA, classical PCA. With the sample, you apply classification. Software, I told you, right? Go for Penny Lane, and yeah, I think Qiskit is having version problem. Qbride, implement all those using Qbride. Qbride is a cloud platform. Qbride. So inside Qbride, use Qiskit, or else directly work in Penny Lane. Okay, locally you can work using Penny Lane. Locally you can work with Penny Lane packages. Penny Lane packages. Yeah. So really, I'm so happy, gentlemen. We have done. We means we Anutantra team done variety of sessions across India. I'm very happy. So you people are very interactive. Really. Yesterday also our CEO told the same. Yeah. So please go ahead. Yeah. So don't work standalone. Combine with one or two departments: mechanical department, ECE department, computer science. Jointly work. Don't work alone. It's very tough. So have a team. Have a team. Sorry. It's team. Then in a team, you people what explore and learn and implement. It is time-consuming process. It took almost 5 years. Yeah. My email. Yeah, let me put my email. prof dot prash at IEEE.org. Yeah, yeah. Really, it was a wonderful interaction and discussion with a intellectual team, I can say. Thank you all. Thank you. See you all. So let me stop.
Rajnarayan sir, Mahalakshmi madam, please propose the thanks message, madam. Ma'am, am I audible? Please mute yourself, madam. Ma'am, unmute yourself. Ma'am, unmute yourself, ma'am. Ma'am, please unmute yourself, ma'am. Sir, host, sir, unmute Mrs. Mahalakshmi, madam.
So thank you very much, sir. Prakash sir. So section is very nice. So again, I'll thank you. Sincere thanks to you. So now we are going to the second section. I'm welcoming Dr. Tilakavati madam to take on the second section. So before that, I'll just give an intro about today's second section resource person, Dr. Tilakavati ma'am. So she is an assistant professor from the Department of Computer Science, Communication Engineering at National Institute of Technology, Tiruchirappalli. Madam has completed doctorate in biomedical signal processing from NIT Trichy in the year of 2022. So ma'am has a ME in specialization VLSI ME, then at Regional Engineering College. Then madam has madam's B in electronics and communication engineering from University of Madras in 1998. So the area of interest is in digital circuits and systems, microprocessor and microcontroller, computer architecture, embedded system design, low power VLSI design, and VLSI system testing. So he's also deeply engaged in the research on biomedical signal processing, AI application in healthcare, IoT, and FPGA implementation and system level compression techniques. So with an immense record of publication in national and international journals, and madam has made a remarkable contribution to both researchers and academics. So her excellence as a teacher and researcher has been recognized with several honor and notable awards, such as Dr. Sarvapalli Radhakrishnan Best Faculty and Research Award in 2022, and conferred during the National Symposium on National Education Policy by IMR of Institute of Higher Education and Research, Vijayawada. He has also mentored students who have brought loads to the NIT Trichy. So had BTech EC project won the Best Final Project Award in 2018. So from this, so Dr. Tilakavati is also an active member of IEEE, IET, and IST contribution to broad professional committee. So I invite our madam to take over the section. Thank you, ma'am. Tilakavati madam.
Ma'am, Tilakavati ma'am, are you audible, ma'am? Ma'am, are you able to hear my voice? Ma'am, we hand over the rights to yourself, madam. The host rights to yourself. Please share your slides, ma'am. Tilakavati ma'am.
Ma'am, please 2 minutes wait, ma'am.
Yes, ma'am. Yes, ma'am. Yes,
Yeah.
ma'am.
Thank you. Thank you for your introduction. Just 2 minutes.
Yes, ma'am.
Two to 3:30 on that session. 3:30 to 5. Yeah,
Your screen is visible, ma'am.
Ma'am, am I visible?
Yes,
Please.
ma'am. Yes, ma'am. Your screen is visible.
Screen is visible.
Yes, ma'am. Please.
There is a movement in the PPT, ma'am.
It was in the first slide, ma'am.
Okay.
Please make it a slideshow, ma'am. Yes, ma'am. Yes, ma'am. The slide is moving, ma'am.
Audible, ma'am?
Yes, ma'am. Your voice is audible.
Okay. Fine. So,
Hand over the session to today's resource person, Dr. Tilakavati, ma'am. Please proceed, ma'am.
yeah. Very. One second. Okay. The very good evening to all. And so this session is related to the quantum optimization algorithm and its application. So, so in order to get into the optimization algorithm, I give a brief introductions about what is the quantum basics, followed by the gates which is used to design the quantum, and the qubit and the tensor product, followed by an algorithm, the basic algorithm of the quantum. And once you understand the basic algorithm, slowly we can move to the optimization algorithm. So this is an agenda of the today's session. So, ma'am, it's audible, ma'am? Ma'am, it's audible?
Ma'am, your voice is audible, ma'am.
Yeah, fine. Thank you. So what is given in the slide? You can see that there is a diagram. So this diagram talks about a number called 0 and 1, and this number which is called as an input. And the input here in the quantum, we used to call it as a Q bit. Usually it's a bit in the classical, and here it's a Q bit. Let me give a brief next slide what do you mean by Q bit. So usually there is a 1, 0 and 1. And in the quantum, there is another bit which is called as a superposition. So, so that is helps for the parallelism. So that's the reason we call, instead of a quit in the quantum, we call it as a qubit. And then the next one, this is called as a quantum circuits. And the quantum circuits are designed with the help of a gate. So the gate is helpful to design the quantum circuit. So when you provide the input to the quantum circuit, you're able to get an output. The output is called as a measures. The measures here, which is represents the classical value, and measures is usually represent as a probability. Like what is the 90% of the probability or 80% of the probability? This is like a classical. So this together, which is you call it as a this is a quantum circuit, and this we are going used for the upcoming algorithms. So when the qubit is given as an input to the quantum circuit, the output is need to measurable. The quantum circuit is designed with the help of a gate. So let me give the brief introduction outline about the gate. So the first is bit, it's called qubit, how it is represented in the quantum. So this is called 0. Usually 0 means 0 in the classical computer. And here the 0 is represented as a 1, 0 in the form of a column vector. So since it's represented as a column, here you call it as a get 0. If it is a 0 in the quantum, you call it as a get 0. And if it is in the row, if the data is in the form of a row, then you can call it as a bra 0, right? It's a bracket. So when it is a row, then it is called as a bra. When it is a column, it is called as a get. So in the quantum, the bit is represent 0 as a get 0 and the get 1. And the representation, the value is 1, 0. For 1 is that 1th position. This is the 0th position and the 1th position. So for 0th position is enabled 1. And for the first position is enabled as a 1. The same way, when you go for the 2 qubit system, for 0, 0, the first position, for 0, 1 is the second position, for 1, 0 is the third position, and 1, 1 is the last position. So the respective position is enabled. It's enabled as a 1. The rest will be a 0. So this is a way it is called as a qubit. The get 0 value is this, and the get 0, 0 value is this. So this is act as an input for the your circuit. Slowly, like in the real time, for example, you can take a video. The video is represented as in the form of a frames. So each frames is represented as this encoded value, like 0, 0, 0, 0, 0, some encoded value, 0, 0, 0, 0, 1. For each frame, this input is for the first frame, and this is for the second frame, third frame. So this is encoded, like each frame input is encoded like this, right? So the respective bit is get enabled. So that is says as a that is the way in the form is in the case of an quantum. So this is about an input. So each input is represented as in the form of an encoded value, and you can slowly call it as a get or bra. If it is a column representation, you call it as a get, or if it's a row representation, you call it as a bra. So this is about an input qubit, right? It's a 1 qubit, single qubit, 2 qubit. It can be any number. And the next thing is I would like to talk about a gate. So the different gates are there. This is called a X gate. The X gate indirectly, which is called as a NOT gate. So the matrix representation, NOT means when you give a 0 as an input, the NOT means it converted into 1. And when you give 1 as the input, it usually converted as a 0. NOT means it's an opposite, right? So it converted. So X gate usually is represented in the form of a matrix like this. So we already saw for 0 position, here it need to enabled 1. Since it's a NOT gate, the opposite, instead of enabling here 1, it enabled here. So that is a matrix representation of the NOT. So this is the matrix representation. This is the pictorial representation of the X gate. right? So it says that this is one thing. When you give an input to the X gate, what is the output? The output it says as 1. So the 1 is, it's measured it as a 1. When you give a 1 as the input, the output is hopefully it is a 0. Right? So this is the nature of the X gate. With this gate only you are going to design a circuit, and this circuit only you are going to use it for an algorithm. So that's the reason I'm starting from the gate. So the next one is called as a Hadamard gate. This is the special gate. This gate only supports the superposition. So superposition is the if 0 or 1, the superposition is says that there is a probability of coming a 0 and a 1. Both. The output can be a 0 or it can be a 1. So that is called the two superposition, and this Hadamard gate, it helps to support the parallelism. So the matrix representation, this is the matrix representation of the Hadamard gate, where 1 by root 2, where the last position it is represented as a 1. So the H is represents the gate notation. So when so here it says that when you give an input 0 to the Hadamard gate, what happens? Let me check. Sorry. So Hadamard gate, this is the matrix representation, and 0, this is the matrix representation. When 0 is gives to the Hadamard, so basically in the quantum, you want to write from the back to the top, back to the front. This is a measure. So you want to write from H, then followed by G. This is the way you want to write in the quantum. So this is a H gate followed by this is a 0 gate. So when you multiple, the answer is 1 by 2, 1 by 2. So this is the position for 0, and this is a position. You see, this is 0 matrix. This is the, so this will give a output as 1 by root 2, 1, 1. So it means to say the 0 is also enabled and 1 is also enabled. So since I already said 1, 0 for 0 position and 0, 1 for first position. Here 1, 1, it means to say 0 also enabled and 1 is also enabled. So when you take 1 by root 2 outside, the output is 0 and the 1. So this you can say as get plus. So when you give 0 as the input to the Hadamard gate, the output is get plus, right? The same way, when you give 1 as the input, the output is get minus. So it indirectly it says that the probability here, the word called probability. So the 50%, when you take 1 by root 2 as a whole square, it gives 1 by 2. 1 by 2 is the 50%. So it says that when you give as 0 as an input to the Hadamard gate, when you send one input to the Hadamard gate, the probability of 0 and the probability of 1 both can come. This is called the superposition, right? So for 0 you get plus, and for 1 you get you able to get minus. So this is about an Hadamard gate, which shows that there is a chances of both a 0 and 1. There is a chance. And the next fellow, which is called as a C0 gate. The C0 gate, it takes 2 inputs. So the 2 input, in the C0 gate, what is the property means? When this is called the control and this is called the target. So this is the diagrammatic representation of C0 gate, where for X gate you put X, for Hadamard you get put H, and for this is a diagrammatic representation where the input is represented by 2. One is called the control, the next one is called the target. So when the control bit is 1, basically the target bit is get flipped, Okay, so that is the property of the C0 gate. So when the control bit is 1, here is the control bit is 1, the target bit is flipped, right? So, so this is the nature of the C0 gate, which is with the help of a 2-qubit gate. And this is the matrix representation. So this matrix representation says that when you give 0, 0, the output is 0, 0. When this is a 2-qubit system, when it is 1, 0, the output is uh, 1 second, 0, 0, the output is 0, 0, 0, output is 0, 0. 0, 1, the output is 0, 1. But 1, 0, the output is supposed to be a 1, 0. Instead, it is supposed to be 1, 1. And for 1, 1, it's 1, 0. So this is the matrix representation. So that's the reason the respective, basically here it's need to be 1. But in the gate of a C0, when it is a 1, 0, the output is 1, 1. So that's the reason the fourth position is enabled. And for 1, 1, 1, the third position is get enabled. So that this is a pictorial and this is a matrix representation. So this is all about the gate. With this gate only, it means to say a lot of gates are there. This is the primary gate. It means X mean when you use the X gate, it became ulta. When it gets opposite, when you use the Hadamard gate, the output can be a superposition. It's both 0 and 1 probability. And for controlled gate, when the control state is 1, it gets flipped. So this with this 3 nature, let me see the quantum circuit. So this is the quantum circuit. So the quantum circuit is designed with HK, HX, right? When you give an input to the quantum circuit, what might be the answer? So the circuit is designed with the help of a Hadamard followed by the X gate. So let me see what might be the cases. When you give 0, what might be the output? Since you are using Hadamard, I already said when you use the Hadamard, there is a probability, right? The output can be there is a probability that 0 and 1. That is the nature of the Hadamard. And escape is also. So what might be happening? So many methods are there for that. So I am explaining another method. So, as this is the case, as I already said, we want to move from the black to the red. So, X, X. So, this is so this is the Hadamard gate. Okay. So this is the Hadamard gate, and this is the input for 0, right? So when you participate, you get 1 and 1. So it means to say the probability of 0 and the probability of 1 is there is a chances of getting 0 and 1. So this gate says that when you give an input to this circuit, then the answer might be 0 or 1. Both the chances are. So can you understand that usually Hadamard gate is 1 by root 2, here also 1 by root 2, and 1 by root 2.
Ma'am, your voice is not very clear, ma'am.
Okay.
Little bit disturbance.
Okay, now can I do one second? One second.
Now it's okay, ma'am.
It's clear now. Just now it's audible.
Your
It's
voice is
audible,
low,
but
ma'am.
some sound is coming back when you speak, ma'am.
Yeah, I don't know.
Ma'am, your voice is
There is,
very low, ma'am.
yeah. Hello.
Yes, ma'am. Now I got it, ma'am.
Now it's audible.
Yes, ma'am.
Now it audible, ma'am.
Yes, ma'am. Clear, ma'am. Clear.
Yes, ma'am. Now clear.
Please proceed, ma'am.
Yeah, ma'am. Yeah, ma'am. Yeah, ma'am. 1 second. 1 second. Ma'am, 1 second. Like earphone, some adjustment I want to do.
No problem, ma'am. Please, ma'am. Dear participants, the resource person is having the audio problem. She's connecting now, sir. Within few seconds, she may join it, sir.
Ma'am,
Yes, ma'am.
audible now?
Yes, ma'am. Clear, ma'am.
Clear. Okay, fine, fine, fine. I stopped sharing. 1 second.
Yes, ma'am.
Ma'am, it's okay.
Yes, ma'am.
Okay, thank you.
We may able to see your slide, ma'am. Please proceed, ma'am. Thank
Okay,
you.
fine. So, the one thing is, what we discussed previously means, 1 second. What we discussed is previously the Hadamard gate here, in this position, you used to get minus. Okay. So this, since you are applying X means the minus will turn into here. So this is a final the output of XH. And when you give a 0 over this, it says that the probability of both the 0 and 1, this is talks about a superposition. So it says that the probability is both 0 and 1 is 50%. It indirectly they both can come. So the same way, when you give 1 also as the input to the circuit, it says that the output might be either 0 or 1. So the same thing, when you're using, when you're giving 1 to 2 Hadamard gates, in this case, when you take 2 Hadamard gate, the output is a identity matrix. So the identity matrix which is says that when you give 1 as the input, the identity matrix is applied, so the 1 will be the output. So when the 0 is the input, the output is a 0. So as a conclusion, now you are giving the input to the circuit. The circuit is designed either to Hadamard gate, and it either be designed using Hadamard, X gate and the Hadamard gate. When you use 2 Hadamard gate, the output 0 for output is a 0, and 1, the output is a 1. When you are using this X and H, when you give a 0, the output, it might be a 0 or it might be a 1. There is a chances both can be there. That is called the superposition. So this is called 1-qubit system, where you are giving only 1 qubit as an input. Now you are going for the 2-qubit system. So uh, for 2-qubit system, slowly the thing is going to the tensor product. So this is for tensor product. So this is 1 qubit. This is another qubit. Between that, you are applying the tensor products. So when you apply the tensor product, nothing. The first variable, it takes the whole thing. The second variable, it takes the whole things. So the first variable and the second variable, that might be the solution. So here, instead of a 1 qubit, you are giving a 2-qubit system. Got it? And instead of a 1 Hadamard gate, you are using a 2 Hadamard gate parallelly, followed by the C0 gate, and again is followed by the 2 Hadamard gates. Right? So this is a 2-qubit system where 2 things are run parallelly. So what happened here is there is since Hadamard, and this is called the tensor product of Hadamard. C0 gate followed by H, a tensor product of H. So let me see what is the output of this. H cross H. So H cross H is, this is for H and this is for another H. So I don't want to explain this in detail. If you want, I can explain at the end of this thing. So this will takes 1/2 the outside. So 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1. So this is H gate and this is an H gate. And this one, I already said tensor product will take this and make a product with this hole. So this, when this red color makes the product, you used to get this red color and the blue and the orange and the green. So this is the output when you are making a cross between the 2 Hadamard gate. That gate is called as a unary gate. So this is called the unary gates, right? So, so, uh, so, uh, 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 so, uh, so here you can see that when you give this 0, 0, you that 0, 0 is, this is a 0, 0 input and it is applied to this unary gate, where is when H over H and this, when you are doing together, you able to get this unary gate. This is called the unary gate representation. So already we have seen the gate like X gate, H gate, and C0 gate. This is another gate which is called as a unary gate. So for 0, 0, output is 0, 0, and 0, 1 is 1, 1, and for 1, 0 is 1. So for 0, 0 is the same thing. What we see, we already discussed earlier. 0, 0 is 0, 0. And 1, 0 is 1, 0, 1, 0, 1. The third position, you is able to get 1, 1. And for 1, 1 is a 0, 1. So this is a thing how instead of a 1 qubit, a 2 qubit is slowly is we are getting into a 2 qubit. And this might be applicable for 3 qubit, 4 qubit. And this is an explanation. I don't want to explain this in detail, where this is talks about a 3 qubit system. Okay. When the gate is designed and 3 qubit is gate, what happened? So this is an intro. The intro is talks about what is called the qubits and what are the different gates, like X, H, and unary. Later I will explain about C0, and the last one is a unary. So this, using this, you come to know how when you send an input to the gate, what might be the output. That's you learned right now. If 0 you said, if you sent 0 to the Hadamard gate, the output is the probability of 0 and 1 both can come. If in the case of an X gate, if you send 0, you able to get 1. And in the case of C0 gate, when the control is 1, the respective target is became flipped. So that's we saw when the input is entered into the gate, followed by we also saw the tensor product. When the 2-qubit system comes into the picture, the tensor product is happened between the gates. So this is an introduction. This intro talks about a gate, and now we are slowly getting into the algorithms. And after this, we can slowly get into the algorithm called optimization algorithm. So the first fellow who, the Dutch is the first fellow. He is the fellow which started designing the quantum algorithms. And what, let me see, this is a basic algorithms. Got it? And this says the beauty of the quantum. This algorithm, which is used to say the beauty of the quantum. So this algorithm, the Decius that algorithm is called the Decius algorithm also. So here the algorithm intention is used to check whether it is a constant or it is a balanced. Right? The two status, whether is a constant or it is balanced. Let me see what is called the constant and balance. So this is for this is called the constants function. So the constants function, whatever the input, the output is always same. You can see the input might be 0 or 1. The output is always same. The input is 0 or 1. The output is always same. It's a constants. The output is the same. Then there is a balanced. Balance is equal number of zeros and ones, right? Whatever the input, the output supposed to consist of equal number of zeros and one. So the digits, the first algorithm which starts to check whether the given is a constant function or is a balanced function. So the constants means always the output is supposed to be the same. Either it can be a 0 or 1. While in the case of a balance, it's either the half of it's supposed to be 1 and half of it's supposed to be 0. So let me check whether it is a constants or balance. So here is the 2-qubit system. So 2-qubit system is 0, 0, 0, 1, 1, 0, 1, 1. And the output here says 0. So this says that it is constant. And here you can see that the output is, there is lot of output can be there. For this input, this line says that there is lot of output. And for this output, you can say that it is a constant. And when it is this, you can say that as a balance. Okay? You can say this as a balance. So this and all, you can say this as a output as a partial constants and a partial balance, right? So this is the status. So when you are sending some input, you want to check whether the function is execute, and you want to check whether it is a constant or balanced function. That's so in the quantum, when you talk about a quantum, they says that in the classical, it starts with the classical. If you are using AND gate, 0, 0, 0, 1, 1, 0, and 0, 1, 1. So if it is an AND gate, what might be the output? For 0, 0, the output is 0. For 0, 1, the output is 0. And 1, 0 is 0. And for 1, 1 is 1. So this is the AND gate output. In the quantum, so in the classical, if the output is 0 is the output, then the input might be 3 cases. Got it? The input is the 3 cases. So here you can say that the 3 queries is required. And if it is n queries is required. But in the case of a quantum, from the output itself, you can decide what might be the input. So the quantum says that there is only one query is enough. In the case of one classical, there might be n number of queries. But in the case of one quantum, it says that it is only one query is enough to predict what might be the input. So that is achievable with the help of the reversible gate. So this is for the AND gate, AND table. As I said, in the case of classical AND, what might be the tabular column. Here, this is an AND for the case of a quantum. So when the 0, 0, the output is 1, 0. 1, 0, 1, output is 1, 1, 1, 0, 1, 1, and 1, 1 is 0, 1. So this says that, so for every input, there is a separate output, right? The same way, this is a 3-bit. You can check that for every input, there is a separate output. So from the output itself, when the output is 0, 1, 1, you're able to predict this might be the input. So with that is called as a one query, that only one query you're able to get answer. So that is this reduce the time. So that's why this is designed, and this is designed with the help of the reversible gate, and the reversible gate indirectly, which is called as a oracle gate. This oracle function, this oracle gates are used all the algorithms, most of the algorithms in the quantum. So this oracle gate, which is also used in the optimization algorithm, that's why I want to say. So here I don't want to get this into a detail. So this is an oracle function UF. So what has happened within this black box for the to check whether it is a constants or a balance? Let me see what it's happened. Okay, for the salon. So I don't want to explain everything in the detail. Okay, so this and all in detail. I don't want to explain. So this is, I'm talking about an oracle phase. So let me start from here. So this is saying that the all slides I'm going to skip. I'm explaining only an essential one. If you get time permit, I will explain this again in detail. So here you can see there is an input. There is the input and there is a circuit which is consists of X and Hadamard gate, followed by the oracle box, oracle phase, followed by the measures. Got it? If you send 0, 0, what happened? Let me see. So here you see here, when you send 0, 0, the X will change it into 0, 1. So here it change into 0, 1. Then what is the output of the 0? Already I said the Hadamard gate, the output of the 0 is get plus. And for the 1 is get minus. So this, in this stage, it is converted as a get 0 and 1. Then what happened to this oracle box? Okay. So so the get 0 and get 1. So this is a representation. And the plus, how you can represent the plus? This is a way you can represent the plus. The probability of 0 and 1 is 50%. So this is for, this we discussed in the previous slide. So this is for 1, this is for plus, and minus you are keeping as it is. And now you are multiplying this. So this is an expansion. 0 minus get plus and minus. Now you are applying the oracle phase. So when you apply the oracle phase inside, okay, so this is a formula that is given detailedly in the previous slide. So this formula says that the X here is called 0, and this is a formula. So this will be converted as a -1. The f of X here is a 0, and X here is a 0 and minus. Okay, so this is for when it is 0. So, and so this is for this value will be converted like this, and this is here I will say this is in detail. So this is a representation for the 0 and this is a representation for the 1. Got it? The previous, the same thing. This is for 0, like -1 f of 0. This is for the 0 and this is for the 1, right? But I said in the constants function, what is the nature of the constants function? I said the constants function means when the 0 or 1, when in the constants function, when the constants function in such a way that both the value is supposed to be same, right? When f of 0, when you give 0 and when you give 1, the output supposed to be 0, right? When you give 0, when you give 1, the output supposed to be 1. So it already I said for the constants function, the output supposed to be same. You see, the output is supposed to be same. So when you are applying this to this, so when you are applying this, you able to get for the constants function, you able to get plus or minus 1 by 2 of this value. And for this is for balanced function. I already the balanced function, half of the thing is need to change. You see, the output is changing. So for balanced function, this is the output. So for constant function, this is the plus or minus 1 by 2. This is the output. And for balanced function, this is the output. So this indirectly this says that for constant function, you're able to get plus, and for balanced function, it's get minus. So as I already said, from the output, you're able to predict the input. In the case of a quantum, because each output has its own output has its own input. So from the output itself, if the output is get plus, you can predict the function which is inside the oracle box is a constant function. And if it is a get minus, you can predict that it is in the balanced function. So this is the thing. This is the thing. The first algorithm, it comes and they used this oracle box, and with the help of an oracle box, the oracle box is placed as the constants or balance, and it used to from the output itself you able to predict whether it is a constants or balance. So the slowly. The same algorithm is extended for n qubit. It's for 2 qubit and it's slowly extended for n qubit. And for n qubit, the same story. So that says that the oracle, even the n qubit is there. Whether to check whether it is a constants or balance, the oracle takes only one query. In the case of a classical, it takes n queries. So this is the same thing, the same story, the same diagram for the n qubit. So this is all slides which talks about an n qubit. So from this, I would like to conclude that the first algorithm is designed to check on constants and the balance. From the oracle box helps to predict from the output, it helps to predict what might be the input. So the oracle takes one. So the quantum takes only one query, while rest of the classical algorithm is used to takes n. So the same, the most of the algorithm which is used this oracle box, it's called as a Grover search, where the Grover search comes under the category called optimization. I will explain this in the detail, right? So apart from another algorithm, this is the algorithm we check, and the Shor algorithm, which and all you use it to see in the cryptographies. So all these algorithms which is designed using this oracle box. So we start with the oracle algorithm. Slowly we can go ahead with the Grover algorithm. Slowly we can get into the Grover search. Okay. So the first Grover algorithm, it's a searching algorithm, which is designed by the Grover in 1996. And this says that it's reducing the searching time. Okay. And the same searching is happened in the classical algorithm. It takes n time, while in the case of when you use the quantum, that Grover algorithm, it takes only the time as the root of n, right? The quantic speed up, it's reduced in the time. So you are searching something. Let me see some example, and I will explain what you are going to search. But this says that a searching time is reduced. So how it is, when you talk about Grover algorithm, so there is an input. When you give the input, there is a Hadamard gate. The Hadamard gate is used to convert, that is the superposition, followed by a oracle box, and followed by the amplification, then followed by the measures. Right? This measures is the quantum, classical computer. So when you give one input here, the quantum, it get recorded, whether it is a 0, if you give 0, whether it is a 0 or it is 1 or 2, this get recorded here, right? So I will explain this in detail. So there is an input, oracle box and amplification board, and followed by the measures. So let me see what happened in the oracle box and what happened in the amplification box. The oracle box is used to find the solution. Okay, oracle box here, which is called check the solution. And the amplification marks, it means to say it finds the solution. It used to do the marking. It used to do the mark the solution. And the diffusion box, which is used to amplify the marks, right? It increased the probabilities, right? So this is the two responsibility. So there is an oracle box and the diffusion box. It's used to mark the solution, and this fellow is used to amplify that respective solution. So in the real time, I'm going to take one of the example is called the frame. The frame which is having the highest motion. Okay, so this is a real-time scenario. For example, there is a video is there. The video which is consists of a frames. Got it? The video is a consist of the frames, and which frame is having the highest motion. That is the so each frame is represented with the using the optical flow algorithm or some algorithm. You able to calculate the motion of the frame. For example, for this frame, the motion is says that it is 5. I'm giving one number, and for second frame, the motion score is 7. I'm talking about the magnitude and the distance, and this is called as H. And this is called as 10. Okay, so among this, the 10 is the highest motion frame. Okay, so the oracle box, what is the responsibility oracle marks? It's used to do the mark. So it used to mark that fourth frame, this frame, right? It used to mark this frame has the highest motion. That is the responsibility. The marking is done with the help of the constraint, right? The constraint you want to write. So the constraint is might be there is the M is the motion when you comes. You can put some threshold. The threshold says if the motion is greater than 100, I consider that frame is the highest motion frame, right? So this is called as a marking, and this marking is that is the highest motion frame. It's marked by the oracle. And this diffusion boxes amplify this. Amplify this means the fourth frame. Yeah, fourth frame is the highest motion frame. Highest motion frames. That way, this used to increase the amplification. So basically, this, right? So this is run in the real time. There is a word called short. SHOT, short. The short means how many times you are running the particular this circuits. So the short in default, it is called as a 1024 shots, right? It means to say 1024 times you are running this circuits, right? So first, when the first frame is coming, so this oracle box says, no, this is not a highest motion frame. When the second frame is coming, it says that no. Third frame is coming, it says no. When the fourth frame is coming, this fellow says yes, this is the highest motion frame. And the amplifier, what it used to say, do means, it gives the the value is 1. First time it gives for first frame it gives 0. For second frame, it is gives 0. And for the fourth frame, it used to give 1. So when the second time you are running, the fourth frame is get the again 1. So when you are running 1024 times, the probability of the fourth frame is says that 90%. 90% means the highest probability. Then the fourth frame is the highest motion. So this amplifier, when you write, it used to amplify it. This fellow is masked and this fellow is used to do the amplification. The amplification is means to say boosting. It gives a particular info, when this fellow says that this is the best solution, this fellow is amplified that. Yeah, this is the best solution. This is the best solution is amplified. That amplification, we are indirectly, it is called as a probability. The probability, 90% probability, 80% probability, 70% probability. That value is measured here. Got it? When the first frame is sense, the measure value is 0. For the second frame, this measures can be there. So this is the things has happened real time. Okay, when you are working with the real application, this is at the back end. So the application says there is a frame. The Oracle box is used in masking. The amplification is used to amplify and give more support to whatever the solution we are expecting. The solution is the best frame. For that is used to amplify, and that then you are using to get one graph. The graph is called the frame versus the chart. That graph says the highest probability for that. The respective bar will be high. That says that that particular frame has the highest motion. So such way you able to find in the case of a quantum. So there is a two thing. It's called as an Oracle box or the diffusion box. This is the way which used to work, right? So this is called the Grover search algorithm. Which one is the optimized frame is used to identify using the Grover search. The Grover search among the frame, it used to highlight, it used to find which one has the highest motion. That is used to be enabled and that is gives the highest weightage. That such way it used to find a good optimal solution. So the next is talking about optimization, where optimization you quite knows about finding the best solution. The solution, it might be a minimal cost or it might be the maximum performance. In the real world, when there is a Google map, right? I want to move from A to B. There is a lot of route will be there. The route is called the solution. Lot of solution is there. So which one is the best solution? In this case, which used to find the minimal cost, minimal distance. Okay. So that is the responsibility of the optimization algorithm. There is a many solution will be there. Among the solution, it used to find the Oracle which used to find the solution. Oracle box is used to find the solution. And among that, which one is the best solution is used to find with the help of the optimization algorithm. In the real-time application you use for the Google Map, many deep learning models and many, like for optimization, many things you use in the real time. So when you talk about an optimization algorithm, these are the classical algorithm is called gradient descent, Newton, simulated and genetic algorithm. So these are the many the classical algorithm. Now I unable to disconnect. I'm having some research papers which use this Grover search algorithm followed by some genetic algorithm together, and they come up with the optimization techniques. Right? After this PPT, I will show that research papers. So this is a classical algorithm, and when you go for the quantum, it's a Grover search. QA, the quantum optimization, approximate optimization algorithm, and the quantum annealing. So these are the quantum optimization algorithm. And now we discussed about this Grover search in detail. So what we discuss is the Grover search. That is, we discuss in how using an Oracle and using a diffusion, how you can find the optimized results. So when you in the Grover, there is only two phases called Oracle and the diffusion. And now we are going for the next algorithm called the quantum approximate optimization algorithm, where the phases, namely initialization, evaluation is called oracle box. The oracle is used to, I already said, it used to do the masking, which one is the best one it used to choose with the help of the condition. So here it used to find the good solution. Followed by, I said there is a diffusion box. Here there is a no diffusion box. Instead, there is called update. Update, it means to say that solution is closely moving to the best results, right? A solution, you are making that solution as the best results, then is the constrained, is checking the rules, then finally is using the stopping. So the first Grover search has only two phases, and here is slowly you are going for update and followed by a constraint. Then finally it's initial and stop is the common, evaluation is the common, and that solution, whatever you are getting the solution, getting the solution is going near to the best solution. Finally, it's the rules. So here I'm just touching this. Practically in my research, I used the Grover search, and I combined the Grover search and genetic algorithm for my research. And we come up with our own research articles. Apart from the Grover search, few more things are there. That's why I'm explaining here. How come it is get varied? So as it's Grover search, initialization is there, and Oracle box. Here, what happened in the case of an Oracle box? It says binary results. It's 1 or 0. Whether there is a best frame or the worst frame, it's a 1 and 0. It's in the case of an Grover. When you go for the optimization algorithm, you able to get the quantum results. Quantum, that number is called some number, right? 23, 25, the quantitative results with the help of this with the help of the gradient descent and with the help of Newton methods and all, the output of the Oracle box, instead of zeros and ones, here it meant the quantitative value, right? With the help of gradient value. It is gradient value, it's used to say the gradient, the best solution. So that is the difference between here and this, and followed by that making that to move to the best solution. That is the third phase, right? This is called the third phase. And finally, the value is get measures, right? So that's the way. So what we've seen is there is the discussion about what you mean by the how about the inputs, and followed by when the input is applied to the gate, how it is behave, and this is the way you can design the circuits. And the first basic algorithm, the basic algorithm is used to check the constants or balance. From an output itself, it able to check the input. So for the quantum is takes only one query. That's that is used to convey it here, and that is designed using the Oracle box. So that Oracle box is, this is an Oracle box, and that Oracle box is used in the case of an many algorithms. And Grover search is one of the, it's not a purely optimization, is one of the optimization, it's a part of an optimization algorithm. And then the Grover algorithm is designed using an Oracle and amplifier. Oracle is, if it is a solution is there, it's set whether it is 1 or 0. If it is the best solution, it says 1. If it is the worst, it says 0. That's that. In amplification, it used to do the increase the probability, right? Whatever the solution says is right. It used to amplify it, right? So in the case of a Grover, it's so when in upcoming optimization, instead of 1 and 0, the value is said to be a number, the quantization value that is calculated with the help of a gradient descent. Or it might be Newton methods, that the quantization value which talks about the best solution. The next step, instead of an amplification, there is this next step which is called moving that solution, a lot of solution, moving that solution against towards the best solution. That is the third phase, followed by the measures. So this is about the lecture. I'm going to stop here, and I would one second.
Ma'am, I just want to ask you one question. Your session, it was very nice, interesting, and you discussed about your research also a bit. But means I am also a PhD student, and I am also interested in that basically.
I haven't showed one paper.
Yeah.
Okay,
Just
it's
I
long.
wanted to you please can you explain that Grover algorithm in short? I didn't understood properly.
Short algorithm.
Grover algorithm.
Grover algorithm.
Grovers, ma'am.
Grover algorithm.
Yeah, ma'am.
Okay.
That diagram you showed, no? That one, please, can you explain?
One second. Is it one second, I put it. One second, ma. Let me put in F5 and yeah, ma, it's visible, ma.
Yes, ma'am. Same one.
Yeah, ma. There is a box called Oracle box, ma. Hello.
Ma'am, your voice is audible, ma'am. Audible.
Yes, you are audible, ma'am.
So this is called a Oracle box, and this is called amplification box. Oracle box is called mark. It used to do the marking. Okay. So I said that there is the real world example is there is a frame, and when you use an optimization algorithm, you able to find the motion value. For example, the motion is of this is 10, and this is 5, 15, and this is 1, and this is 0. So this is the highest motion frame. So this says that here is the highest motion frame, and this Oracle fellow, what it used to do now, this used to give this used to mask this. The second frame is the highest motion frame. The rest is it not mask it. Okay. The rest is not mask. Only it's used to mask it among the given input. It used to mask whichever is our expectation. Our solution is that we want only the highest motion frame. So when the motion is high, using the constraint you can able to design. For example, here is the 15, and here I said the threshold is when the value is greater than 7, 8. So here the motion is 15, and 15 is greater than 8. So that's the constraint. With the help of a constraint, it able to mask it. It able to find the solution. For among this, if you able to find the solution, and amplifier, right? This is run not one time. This is runs 1024 times in default. Okay. The first time also it need to say second frame is the best. The second time also it need to say second frame is the best. If I run 1024 time, it need to say the second frame is the best. That is called the probability. 90% this is the best. And the rest is it not supposed to say it's the best. Okay, so that's we used to draw one graph. The graph is called a frame versus short. A short is called how many times you are running. So if I run 1024 time, it says that the second frame, the probability is high, right? So that is called amplifier, is amplify it, right? So the amplifier, so this finds the solution, and this fellow is used to amplify it. So that is the two things which is in the case of an Grover Gadam. This is get measured in the measures each time when you are running. So when you run each time, for the second frame alone, it gives the value as 1, 1. For the rest of the frame, it says only 0. For the second frame, it says 1, 1, 1, 1, 1. So it means to say second frame is the highest. So this is a search among the thing. It's searching which one is the best, which one is the optimized one. Hello, am I audible?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Ma'am, one thing I want to ask, this search algorithm is like a Google search engine, or which thing we can search it?
Google search means I not get the right, what is in your mind. The
What does
searching algorithm is, no, the searching is, normally you can say, um, uh, what to say, like, here my search is which one is the best, that is my motto. Right? When it is, basically what it's happened behind is, when this is, that is also comes under the category called shorting algorithm. When the input is, for example, when it is unshorted, it is make it into a shorted, then from that it used to find the best one.
Okay, got, ma'am. Yeah. And for machine learning, what can we use? Means for deep learning or machine learning, we can
Machine
use it.
learning, I don't have the slide now.
Uh,
Basically, there is a convolution layer is there, right?
yes, ma'am.
Basically, it's a convolution layer. There is a quiz kit is there. One of an stop sharing. So convolution layer, the convolution layer, there is a convolution operator. There is a filters, right? So here, in the case of a quantum, that is represented in the case of a circuits. Hello.
Yes, ma'am.
You see, once again, I'm browsing. I'm browsing and I will show like the right thing. That slide is missing, basically.
Yes, previously, ma'am, that Quizit means one two research person, the speakers, no, they have given us little bit idea about that. Few research person about Quizit, and
Quiz
then
kit.
one
So
penny
there
lane
you
is
can
also
see,
there.
there you can see, when you get into that, now I don't have, one second, I'm just checking. I'm in the quiz kit. One second. Where the convolution layer, right? That layer itself is designed like a circuit, H gate, this gate only, whatever I said to you, right?
Yes, ma'am. Yes.
The same way it used to design. So that is another slide. Basically, I'm in my home. So otherwise, I would have shown that to you.
Yes, ma'am. We can at the end. Please, can you share your email ID? So if I have some queries, me participant have any doubt, they can ask me on mail.
Yeah,
Or anything regarding research also, if we want any help. So it would be.
ma'am, can I share can I share it mm, in the chat? Hello?
Ma'am?
Can I share my ID in the chat?
Sure, ma'am. Ma'am, we'll share that, ma'am. We'll share that.
Okay, ma'am. You can get it from the coordinator, dear.
Okay, ma'am. Thank you.
My
And
mail
then
ID, basically, like it's available in our profile. In the meantime, ma'am, the ma'am will say.
okay.
Shayali ma'am, that entire detail what ma'am was took that the PPT and then a video screenshots and then ma'am detail everything will share you, ma'am.
Okay, yeah.
You
Thank you
can,
so
Possible in the yes, ma'am. Thank you, ma'am.
if you want, I will, one second. I'm going to that, 1 second. Ma'am, can I share the PPT?
Yes, ma'am.
1 second. This is not coming.
Two more questions was in chat window, ma'am.
Okay.
Ma'am, can you suggest how quantum computing used in VLSI design? Which tool to be used? Can this be used for analog circuit design also?
1 second, ma'am. I will say, complete this. Ma'am, dear, this is visible.
Yes, ma'am.
So here you see like a
Discrete ecosystem.
Qiskit QCNN. This is a CNN. This is called QCNN. Cooling layer, convolution layer, everything is there. How about a convolution layer? This is a gate for that. This is an Hadamard gate. What I said that H no entangling, that is, this is called the Hadamard gate, followed by C0 gate. So instead of that filter or instead of that you use it in the deep learning, now this is designed in the form of a gate. Got it? And this gate code is already available as a ready-made. You don't want to write this thing. If you want CNN, this for Grover and all, everything is available. So you can take and make use of it. You see this, this is for convolution layer where they used IZCX. So this is a thing which is talks about a gate. This gate and the respective code. Right? So basically in the deep learning, you have a filter and the convolution operator is applied over that. So here is replaced with the help of a gate, and the gate where the basic is the C0, Hadamard, all entangling, everything is there. And this is a code which is related to convolution layer, where this and all is talks about the respective gates. So, so if you want to implement this convolution layer, you can take only this gate design. Even you can design this your own gate. Got it? So
Yes,
this is
ma'am.
the
We can
extra.
use for classification and all this, no? Like
All this,
normal CNN.
all this, but when we this and all that exam pooling layer, this you can make you when you study you able to get it detail. Instead of an operator, this is replaced by the gate. That's very simple. And internally, if you go inside also, we don't know that much in detail. And hello.
Okay,
Because
ma'am. Yeah,
we
yeah,
are,
I'm
because
listening, ma'am.
we are using only classical computer.
Yes,
When I execute execute the quantum algorithm in the classical computer, even time based, the time I'm not it not running faster. When I calculate the time is as it is taking it as a classical computers and all. The reason is the algorithm we designed, algorithm is working, but we are working only in the classical computer, not in the quantum computer.
yes, but it will take more time as compared to that.
Yeah. But the papers and research papers, everything is get accept. If you use any quantum algorithm, the quantum gates, which readily are available in the QSGIT, but instead of that, you can write the Python code. So you, if when you use QSGIT and all, you have only limited permission. So instead, you can write it in the here Python code.
Okay, okay. Great idea, ma'am. Thank you so much. It was very nice session.
Thank you, ma'am. If any doubt, you can ask me at any time.
Yeah, thank you, ma'am.
Ma'am, two more questions in the chat window, ma'am. Can you suggest how quantum computing used in VLSI design? Which tool to be used? Can this be used for analog circuit design?
Ma'am, so So whatever I said today is like quantum annealing and the quantum optimization, quantum approximation optimization algorithm. So that we discussed, right? That are the optimization algorithm which is used in the VLSI circuits. And the tool as of now, we people is worked only using this Quiz-Kit, and another is Pennyland. So simulator we used it. Not in deeper simulator level. We moved moved our worked with the. It means to say only the simulator and an algorithm level we worked, ma'am. So most probably the tool here also they're suggesting like the same algorithm, or you can use this Quiz-Kit. The VLSI point of view, I not get that much clear. Like algorithm level, I have an idea. So a CMOS tool, I'm not sure about it, and that tool might be available in the case of a VLSI. So algorithm level we worked, and algorithm level we got an output, and for that whatever the thing which it is discussed, the same thing is can also be used in the VLSI.
Thank you, ma'am. One more question from Harshita. Yes, I think she might have posed the same question. How superposition entanglement enable the quantum advantages? The challenges of quantum error correction and decoherence, the types of problems in quantum computers are suited to solve, and how the quantum computing impact the fields of drug discovery and material science, finance, and AI.
Ma'am, question is very lengthy.
Of course, madam. She was typed more
I'm
than a
not.
paragraph.
Yeah, where is the chat? I'm just searching. Here, I not understand the question basically. Ma'am, where the question is posted?
Harshita SP, madam. It was in chat window.
More option.
She may ask the multiple question in a paragraph, madam. How superposition entanglement enable the quantum advantages?
Basically, whatever you asked, that the chat I'm searching in. 1 second. Okay.
5 to 6 messages before, ma'am.
Okay. Okay. How superposition and entangle enables quantum advantage? Okay.
She might include whatever the words known in the quantum computing. I thought that right.
Like all the people is initiated the work in the quantum, and it's very Ashita. Basically, like we like implemented stage. Sorry, like since my research is related to the video, I tested for video and explained with that example. For drugs, and I don't have that much idea, dear. Sorry. Error correction also, that is going in the everything is going in the different direction basically, not in the single direction. Everything is going in the different direction, and even like right now we are working for that cryptography security wise. We working like SOAR algorithm and all works, not like it's moves to the error correction and all this. So I unable to answer as application point of view, dear. We say seriously. If I get time tomorrow, I able to find the solution and I will say it. That's not a problem. But now it's not striking me. Sorry. In the perspective of two things, it's a error correction, and the second one is related to how it for the different application. That 2 point, I need the time to think. That's sure. I will share that answer to your coordinator tomorrow. Definitely.
Sure, ma'am.
Ma'am, you can
If
note
time
down. I
permits, you
will.
may join on tomorrow, madam. Last day. The
Okay.
valedictory session, you may join, madam, if possible.
Yes, sure, ma'am, sure.
The last thing she was asked that what is the impact field of drug discovery, material science, finance, and AI? That is how quantum computing makes an impact on the specific field, that emerging fields. She was asked like that. The final question, I think.
Uh, um, Drugs and all. May I know the nature of your input, dear Ashita?
Harshita ma'am, are you on the line?
Yeah, ma. Audible.
Professor Ashita ma'am? I think she is not in that line, I think.
If I know the input nature, I able to able to reply you. Because we apply lot of quantum algorithm. We know what are the different quantum algorithm which is ready-madely available. So according to the input nature, we take that respective algorithm and used to apply over it and find the solution. So if I know the input in in detail, I can suggest the respective quantum algorithm to you. So nature of important, what if you take a drugs, what you are expecting, what is your target, that and all I want in detail. So where
Through
Harshita
phone
is
call,
not-
we'll contact Harshita ma'am and we'll share your details. She'll come back to you, madam.
Okay,
I think
ma'am.
she may not in that line.
Okay. So hopefully, I think I might done my work. If any doubt, you people can mail me or contact me at any time, right? So the session is went from the basic. First, you want to understand the circuits. Once the circuit you understand, with the circuit you can with gates. Then with the gates you can develop the circuit, right? That circuit is you are using for either the convolution layer. That circuit is you are using for Shor algorithm, namely for cryptography. The same thing might be used for. So the circuit is designed with the help of an adamant, oracle box, and all those things. So that's I covered today. Right? Hopefully, it's. I think I conclude my session.
Excuse me, ma'am, a small doubt, please.
Yes, ma'am. Lavanya.
Ma'am,
Yeah.
actually, yesterday they have given code composer, no, IBM. There we can have Hadamard gate and T gate, S gate and all. But X gate is not available, ma'am. For limited circuits, what you have given some examples, no?
Yes.
Today, you have given some examples, no?
Yes.
There, along with the Hadamard gate, we are using X gate, na?
Yes.
But in code composer, X gate is not available. Can
Yes.
you let me know any other composers available, please?
You are fine. In Quizgate, Xgate is available, ma'am.
Just now I opened this code composer studio, ma'am.
Okay.
But there I didn't see any X gate. There actually it shows Hadamard gate and XOR symbol, connectivity, and identity gate.
Ma'am, what you said? What the resource you said, ma'am?
IBM Quantum Platform. IBM Code Composer, madam. IBM Composer.
Ma'am, IBM is a Quizgate, and there only I saw Xgate.
Okay. And root X and root X dash is there, ma'am. U is there, RX is there, RY is there. But I didn't find there in the.
Xgate will be in the terms of plus sign.
Ma'am, sir, excuse me.
Sir, Karthik sir, mute yourself, sir. Yes, ma'am. Proceed, ma'am. Proceed.
Xgate will be represented in terms of plus sign, not in X.
In terms of plus sign, sir. Okay.
But when I'm using it, showing basically I'm not using IBM.
Okay,
I'm using only the Python code, ma'am.
Okay.
The only reason is for that resource, when you submit a single request, no, you are unable to get the answer. So we stopped using all the. I'm not talking against to something. Sorry to say this. Sorry, I don't know whether I'm talking rightly also. The one thing is open source. We have started to use it, ma'am. So where we all this gate is available.
Okay.
So
what's
like
that open source, ma'am?
Open source is the Python which we are running in our own hardware.
Okay,
So
okay.
there the request goes to there. Again, here also request goes to there only. But but there in the Python code, you have all these things.
Okay, okay. And
Purely as a Python code.
from GitHub itself, ma'am?
Ah.
Okay. Thank you, ma'am. Thank you once again. Very nice and very informative session and interactive session also. Thanks a lot for your valuable time and all.
Thank you. Thank you very much, ma'am.
Madam, your ID.
Where do we run this Python code? You said it is open source. It is using Jupyter Notebook.
Yeah. Yes.
Okay, so different types of circuits can be designed.
Yeah. Yes. 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 You can design your own circuit also. That is shows in the diagrammatic also.
Okay. Okay.
Okay. Everything is available. You open Jupyter or in the Python code, you can run it. The reason is we have our own hardware. No, I don't want to get into that level. I'm moving in the different direction. No, no. So like you can work in the Python, right? That's
okay. Thank you, ma'am.
Yes, ma'am.
Thank you, ma'am. Your mail ID was shared in the chat window. Ma'am's mail ID, resource person, Dr. Tilagodi ma'am mail ID was shared in the chat window. If any other clarification needed on that, you may contact through her mail ID, madam.
And as from another thing, apart from EC department, computer science department is also working. If you want, I can share another ma'am mail ID also. For her, apart from Tilagavati ma'am, you can contact her also. She also helps you. She is from computer science background. Okay, so she is my colleague. If you want, you can also put a CC to her also. So she also helps you.
Sure, ma'am. Sure, ma'am.
Okay, so that is shared in the chat box. She belongs to the computer science. So we people discuss and we used to work, and both you can contact. Any doubt, we are
Ma'am,
ready to
share her contact who is overall working in quantum computing with her friends mail ID also she was sharing. Thank you so much, ma'am. Thank you, ma'am.
Okay.
Dr. Rashekar sir,
Yes, ma'am.
please propose the vote of thanks message, sir.
I take this opportunity to sincerely thank you, ma'am, for your nice lecture on quantum state, multi-qubit system, quantum chemistry, and Hadamard Gate. Your clear explanation and the way you connect fundamental principles with practical quantum computing concept have greatly enhanced our understanding. This session not only deepened our knowledge, but is also inspired us to think about quantum mechanics and computation in more structured and logical way. We are truly grateful for the time and effort you have devoted to enlightening us. Once again, thank you, ma'am.
Okay, thank you for. So I would thanks the coordinator who invited me and give me the opportunity to express, to give the chances to me, right? And followed by all the faculty members, right? Today is a Friday at the end of the day, and everybody, like at 9 o'clock, everybody is with the same energy, right? So it's been good, and thanks to all the participants for patiently listening my talk.
All the questions you have answered very patiently, madam, because you are saying that the weekend itself they are asking some more doubts on that. Your explanation was satisfied with that participants, madam. It was awesome, madam. Thank you so much, madam.
Thank you. I don't know how the question is raised for the previous 4 days.
The same method they are asking the questions, but today is more questions when we compare with the previous sessions.
Okay.
So they are getting a more understanding about that. So that's what it might be a more discussion and fruitful session on that.
Okay. Since my camera is not on, sorry. Right, ma'am. Thank you for all, and thanks to the coordinator and the participant. Thank you.
Thank you so much, ma'am. Thank you.
Thank you.
You may leave, ma'am. Thank you so much, ma'am. The participants are requested to fill your attendance cum feedback form, which was posted in a chat window. Please fill your feedback form. Based on your attendance percentage, you are eligible to write the tomorrow's examination. Tomorrow is the last day. We are posted the schedule in a chat window, as well as the same thing will be posted in your WhatsApp group also. The session will be started at the time of 2 p.m. itself. Tomorrow we are having a 3 sessions, 2 to 3:30, 3:30 to 5, and 5 to 6:30. Afterwards of 6:30, we are having a valedictory section. Once the valedictory is completed, the examination will be started. That should be attended only in your registered portal. Where you are registered your FDP, that same portal itself, we are going to attend your examination. This is for your kind information, professors. Thank you. Thanks for your patience for the past 5 days. Tomorrow is the last day. We have to enjoy on the sessions and we'll complete successfully on tomorrow. Thank you so much, professors. Thank you.